All right, welcome to another episode of Science with Surbeck. Today what we're going to be talking about is motion. So before we get started, there's a couple objectives that I want to outline, and then we'll get into our notes. So the first objective is to determine how a frame of reference is used to describe motion. The second objective is to determine the difference between speed and velocity. The third objective is to determine what you need to know to find the speed of an object. And the fourth and final objective is to determine how you can utilize speed by using graphs. So we get started here with notes with the term motion. And motion is just defined as an object's change in position relative to a reference point. So with that definition in mind, we also need to have an idea of what a reference point is. And all a reference point is an object that stays in place. So if we put this all together, I have a picture that really ties all this concept of motion. So the snowboarder, and this is multiple pictures here, but the snowboarder is in motion in accordance with these reference points, which we could consider those trees in that background. So this snowboarder is moving from one direction to another in reference to those stable objects as those trees. Now, a frame of reference is another term that we need to know, and a frame of reference is just a system for specifying the precise location of objects in space and time. So if we go back to this picture here with the frame of reference, again, all this is saying is, hey, this snowboarder is moving downhill in reference to that tree that's staying in place. So it's just describing the motion that is happening with that reference point. Now, to go a little bit further into detail with this frame of reference, what I want you to know is that when an object changes position with respect to a frame of reference, we consider that object to be in motion. Now, to go one step further with this point that we just made here is that this object in motion is going to be described with a reference direction. Something such as north, south, east, west, or up, down, left, right. We have to describe where that motion is going. So if we tie all of this together, again, we've been talking about this picture of the snowboarder. So the snowboarder, again, as the snowboarder moves down the mountain, the snowboarder is, again, moving down the mountain, and that reference point is those trees that are in that stable position. Okay, so now we have a brief background on motion, and so what we're going to get in the details of is the specific details of what makes up motion in terms of the physics side of the house. So I'm going to change pages here, and we're going to talk about distance. So distance is just described or just defined as a measurement of the path taken of how far an object moves. Now, for us to use distance, it's going to require the measurement of length that the object took, or how far did it go. So to be able to measure distance, there's multiple means, but often the common things are a meter stick. The other thing that we commonly use to measure distance is an odometer. And the odometer, remember, is in your car, so as you drive, you see that number of miles or kilometers, depending on where you are, go up as you drive forward. And then another thing that we can use to measure distance is a GPS, or a global positioning system. Now, again, these are only 3 examples that you can use to measure distance. There's obviously a lot more things out there, a lot more tools that you can utilize to measure distance. So now that we have distance, or an understanding of what distance is, we can move down to this term known as displacement. And so what displacement is defined as is that it is going to measure the change of an object's starting position and ending position. So displacement, and it'll be better explained in the example I have here, but there's two requirements for displacement. One is the distance, and the second thing that it involves is the direction. So the best way to see this is another example here, and I have the soccer field example. So let's say you're playing soccer and coach says, hey, hit a lap or take a lap. Well, you start out here right by the goalpost and you run all the way around, and then you stop right here where my finger is at. Well, your displacement is the total distance that you moved. So even though you've ran almost an entire lap around the soccer field, your displacement is just that distance from the arrow. And it would be right behind where you started. So you could say, for example, the displacement here of yourself would be 15 meters behind your original starting position. So keep that in mind as we keep describing and going through examples of motion. The next thing that we are going to talk about is speed. And speed combines what we've talked about already with motion and with displacement. So simply put, speed is going to describe how fast an object moves. And with speed, we actually have a formula, a mathematical formula, that we can use to calculate the speed of an object. And so the formula for calculating speed is going to be the distance traveled divided by the time that it took that object to travel that distance. Another common way that you could put this speed formula is like this. Instead of having that division symbol, you could simply make this a fraction where you have distance traveled on top over the time it took to travel. Now, with our speed, it is going to be graphed as a distance versus time graph. Now, another term that's really closely related to speed is velocity. And velocity just describes how fast an object's moving and the direction that it is moving. Very important difference there. Velocity describes the direction the object is moving. And so the real benefit about using velocity is that it provides more details, or it's more specific and useful than just speed alone. So let's put the velocity example to an example here. So let's say here, now we have this graph, and again, it is a distance versus time graph. And let me zoom in a little bit here. Let's say you have a car that's moving at a constant speed. Say you're in a race car and you put that pedal to the metal and you're moving at a constant speed. With something that is moving at a constant speed, your speed is going to remain constant. So if your speed is remaining constant, one thing that is changing is your velocity, because as you move, as you drive typically, you're going to be moving direction, and because you're changing direction, even though you're staying at the same speed, you are actually changing your velocity. So the important point about velocity here is that if speed or your direction is changing, your velocity is changing in some way, shape, or form. So now that we have this speed versus velocity business in mind, what we can do, we can get a little bit more into details of what we talked about right there at the start. And hopefully I'll have some more clarity about what we talked about at the start of the notes. So what we get into here is talking more and more about these reference points. And so what we'll do, we'll define and we'll describe some of these different reference points that we will use. So the first thing here is a fixed reference point. Now, a fixed reference point is one in which that is going to remain constant or is going to remain in the same position. So a great example of this is a stop sign. A stop sign is driven into the ground and it remains in that same spot. So a fixed reference point, if we're referring to that stop sign, it could be something as simple as east of a stop sign. Again, fixed reference points, they stay in the same location. Now, on the other side here, we have the line of motion reference point. And what this describes is the direction that is described either needs to be positive or negative. So to help describe this a little bit more clearer, what I have here, an object that is moving in the same direction as travel is considered to have a positive velocity. Now, a negative velocity is when an object is moving in the opposite direction as the motion of travel. So to help describe those two things here, I have a picture. So let's say this person on the boat decides to get up and the boat is moving from left to right, and they start to walk towards the front of the boat, and because they are walking in the same direction as the motion of the boat is moving, they have a positive velocity because, again, they are walking in the same direction of travel as that boat is moving. Okay, so now we get a little bit more detail here, and that is with our combined velocity. So the combined velocity is defined as the overall velocity of all components within an object. So an example of combined velocity would be a bus with students or people on it that is traveling 15 meters per second to the east. Now both the bus and all the passengers are traveling 15 meters per second to the east. So now a little bit more complicated of a term or definition here is the resultant velocity. And so the resultant velocity is the sum of all given individual velocities. So the best way to think about resultant velocity is through an example. So let's go back to that bus example where I said, hey, the bus is moving 15 meters per second to the east, and that means both the bus and the passengers, if they're sitting down, are moving at 15 meters per second to the east. Now, let's say that you get up and you start walking towards the front of the bus as it is moving at 15 meters per second to the east. What happens here, and I'm going to try to zoom in as much as I can, what happens here is this. Because you are walking forward along with the bus moving in that same direction, the resultant velocity is the combination of both your walking motion and your direction or movement due to the bus. So again, let's walk through that example. Someone's moving towards the bus that is moving 15 meters per second to the east. They're walking that same direction. Their resultant velocity would be a combination of those particular movements. So in that example, because you're moving in the same direction as the bus is moving, it would be in addition. So the resultant velocity, and I'm getting crunched for room here, I'm going to label that as our RV, the resultant velocity, would equal 15 meters per second plus the 1 meter per second to give you a resultant velocity of 16 meters per second. And I ran out of room, but that should be 16 meters per second to the east. Now, let's say that you just got on the bus from the bus stop and you're walking towards the back of the bus in an opposite direction as the bus is moving. This time, your resultant velocity of yourself, the velocity that you are moving, would actually be 15 minus 1 because you are moving in the opposite direction as the bus is traveling. And so that's how you see that the resultant velocity of yourself would be 14 meters per second to the east. Now, how we go about this, and one of the most important things here is calculating speed. So what we're going to do here is we are going to go over how to calculate speed. So again, just as a reminder here, that speed describes the distance traveled over a specified time. Now, to calculate speed, you must have two things. The first thing that you must have is the distance the object traveled. The second thing that you must have is the time it took for that object to travel that distance. Another thing with calculating speed is really important is that the SI unit, or sometimes we call this the metric system, is meters per second, or m/s. Now, a term I just want you to know with this concept of speed is constant speed is referring to equal distances traveled in equal amounts of time. So, for example, if you were traveling at 67 meters per second, every single second you would travel 67 meters. Now, moving on down to average speed. So, average speed is just defined as the calculated distance divided by time. So with average speed, we're just looking at, well, how fast did it go over a designated period of time. Now, the speed formula, again, is going to be distance divided by time. Now, one thing I want you to get in the habit of is this. We can just as easily take this formula for speed and we can use it as our formula for velocity. So velocity can be the same thing as distance divided by time. The only difference, the only addition that we need to add to that of velocity is that we need to put a direction of travel in that portion with velocity. So notice how they're the same thing. Velocity is going to have one extra step. So to calculate speed, I always like to have our steps written out so that way we can reference something as we go through and we do actual problems. So the first step is to write down the formula used to calculate velocity. And I know I have speed here written in the notes, but we're going to try to stick to velocity. So that velocity formula, if you want to abbreviate things here, V for velocity equals distance divided by time. Now, the second step is to determine any known values given in the problem. An important thing here for the second step is include the units. This is very important. Now, the third step is to determine any unknown values or variables that need to be found. Then, once you know those unknown values, you may need to have some conversion. So, we're going to try to keep distance in the units of meters and time in the units of seconds. And again, to help you out here, just in the parenthesis here, our D for distance, we're going to try to keep in the unit of meters. And then our T for time, we are going to try to keep in the unit of seconds. Now, the fifth step is to insert what you know into that formula. And then that sixth and final step is to solve mathematically and make sure you include the correct unit. Now, with the business of conversions, I realize some of us haven't gone through that, so I will help us get through that conversion for the processes that we will do. So, what we're going to do now is we are actually going to do an example of how to calculate velocity. So, we have a problem here. We have a lion that is moving due east at different speeds. Over a period of time, it is going to travel 25 kilometers in 4 hours. What is the average speed for this lion? And then what is its average velocity? So, with our conversions, what we'll have to do here, I said, hey, I want everything in meters per second. And so what we need to do first is we need to write down our formula. So for our average speed or for our average velocity, remember our v for velocity is going to equal d for distance divided by time. Now, our velocity would be in meters per second. If you read through this problem, there is no meters per second. So right away, because there's no meters per second, that becomes our question mark. Now our d for distance is 25 kilometers, km. And this kilometers, we need to convert it into meters. So over here, I'm going to write out that 1,000 meters is in 1 kilometer. So what we do is this. We set up what we call dimensional analysis, and on bottom we always want our units to cancel. So on bottom we're going to have 1 km. Again, km is looking to cancel, and then on top we put the m for meters. Now over here, this conversion factor, which I will give to you, or you can look up online, it says, hey, 1,000 meters is to every 1 kilometer. So we are going to need to multiply that number by 1,000. So to show you this calculation, I got my calculator. I'm going to take 25. So 25, and then all you have to do in this case is times 1,000. So times 1,000. That gets me a value on my calculator of 25,000 meters. So I'm going to write down here that our distance in meters is 25,000 meters. Now our time, if you look here, again, we're looking for anything in time. We have 4 hours, and I'm going to abbreviate hours as HR. Now, again, if you think back to the steps, I need this in meters per second. So we first have to break down an hour into minutes. So again, we set up our dimensional analysis, and on diagonals, diagonal units always cancel out, and so we're left with HR for hours, and we first have to convert 2 minutes. So now, let's say we have 1 hour, okay? How many minutes are in an hour? Should be thinking there's 60 minutes in every single hour. Now, is minutes in our units of second? No. So we have to do one step further. We need this unit in seconds. So what we do is we cancel out diagonal units. So again, minutes has to go on bottom here. And then we can finally get to seconds, which I'm going to just abbreviate as an S. So for every 1 minute, how many seconds go by? 60. And so we have our conversion. So once again, I'm going to take out my calculator here, And I'm going to take 4 times 60 times 60 again. So in 4 hours, there is 14,400 seconds. So that becomes our time. All we have to do now is plug this formula into our average speed or our velocity formula. So our velocity, this right here is just going to be the number of meters, so 25,000 meters divided by 14,400 seconds. So what I need to do now is this. I need to go 25,000, and this line, like a fraction, is just saying divide. So I'm going to divide that number by 14,400, and I get this decimal number. All right. So over the course of this time, this lion, and I'm going to round to two digits. This lion was moving at 1.7 meters per second. Now, if I just ask you what was the average speed, this right here would be the average speed. But I want you to find the average velocity. So the speed stays the same at 1.7 meters per second. And the only thing that we need to add in is the direction of travel. Now in the problem it said, hey, this travel or this line was traveling due east. So all we got to put for a direction of travel is due east. And this right here, what I just wrote down, becomes our average velocity. So right here, those become our answers. Now, I will help you work through those conversions because it's something new and that we haven't done a whole lot of. So now that we have the problem done, we can move to our final page of notes, and that is what we call instantaneous speed. And so instantaneous speed is the speed of an object at any given time. So the big difference here is that at that point in time, we want to know how fast you're going. That is instantaneous speed. And now this is measured by determining the distance traveled in a shorter time interval. And so average speed, again, that is over an extended period of time. This instantaneous speed is looking at that snapshot of what is the speed currently of that object right now. Now, something else to note here is this. The smaller the time interval, the more accurate the speed measurements are. So a great example of this is that speedometer in your car. It's going to show the instantaneous speed that you're moving at that given time period. Alright, so the last major topic that we're going to talk about here in section 11.1 is how to graph velocity. And so there are 4 points I want to make before we move to our example here. And so graphs of velocity, they're going to show the distance as the dependent variable, and that is going to be displayed on the vertical or the y-axis. Oh, and I made a blunder here. The distance, which is displayed on the vertical or y-axis, is the dependent variable. Oh, that's my fault. It is the dependent variable. Again, distance, the dependent variable, is displayed on the vertical or y-axis. Now the time, which is the independent variable, is going to be displayed on the horizontal or x-axis. The third thing is that a velocity graph is known as a distance versus time graph. And then that fourth thing is that the slope of a velocity graph, or distance versus time graph, shows the speed of an object. So again, just a reminder that distance is the dependent variable, and it's going to be displayed on the vertical or y-axis. So now what we have here is this. We have an example distance versus time graph. And so what I am going to do here is I'm going to zoom in after I read the question. Is we want to determine the slope of the distance versus time graph. So as I zoom in, and you have this clearly on your notes, we have this particular graph. Okay? And so as we have this graph, the slope, if you remember from math class, the slope is simply the rise over the run. So the slope for us, we want to determine how much the graph rises, divide that by the run. So this is really nicely done for us. I already went ahead, I picked some points here. And so from this point here to this point here, we want to count first the rise. So the rise is going to be, and we have to be very careful, it is going to be 2 meters up, 4 meters up, and then we get to that same vertical line, and it's going to be 6 meters up. Again, that displays that right here. And the reason I went by 2s is because of my graph. So I went 2, 4, 6. So that means the slope of the line is going to be 6 meters, and it's going to be divided by the run of the line. Again, we're going from this point over to this point. So again, check our graph, make sure we're on the right time frame. So each box is 1 second. We have 1, 2, 3. So the run, or the left to rightness of our graph, is 3 seconds. If you take 6 meters divided by 3 seconds, the slope of the line, which equals our velocity, is going to be 2 meters per second. So slope is going to equal speed, which in our example here, 6 divided by 3, is going to be 2 meters per second. And that right there becomes our answer. All right, so that concludes another episode of Science with Surback. As always, I hope you subscribe.